happens? Well, that's an indeterminate form. That's like getting 0 over 0 in Cal 1 or infinity over infinity. It's the same thing. It's indeterminate. So right now we don't know what the result of this is. We have to do more work. L'Hopital is what we're going to wind up doing, but L'Hopital only works when you have 0 over 0 or infinity over infinity, which we don't have. So my Cal 1 students will know what I'm talking about here. We had all these different indeterminate forms, and for each one we had different techniques. If you took Cal 1 elsewhere, right? How many of you didn't see L'Hopital's rule? I think I have asked this before. How many of you did not see L'Hopital's rule? Everyone saw it? You think? Pretty sure? Okay, but I don't know how it was taught, so the way that I approach this might sound different, but you're going to have to let me know if it's like, oh, whoa, this doesn't look like anything I've seen, okay? So we got to keep working here. We're not close to being done here. Yes?
Can you assume it goes to 0 since it's growing exponentially on the bottom and being just multiplied by the same number on the side?
You could think about the rate of growth and say, okay, that is going to be growing much faster than that is. Well, not growing. This is going to shrink faster than that one because it's exponential as opposed to linear. You could deduce that logically, but again, that kind of, to me, that circumvents. What happens if I give you something where you can't see that? Like what if you're in a differential equations class and you've got this is exponential and that's exponential as well. That's exponentially going to infinity and that's exponentially going to 0. Are you going to have a method to figure that out? So I want to see method. On a test, I want to see method. I want to see you get to L'Hopital at some point. All right, let's not forget that all of this is still here, right? We've taken a detour. We're at the little rest stop, right? Having snacks. So I've got to figure this out. This one I don't care about. So now what I'm doing is another problem where I'm going to say, all right, let me isolate all of my attention to this here and see if I can't figure out what to do, right? Because that's the one I'm having trouble with. See, this is where I was saying, students will tell me that this is 0 on a test, and it may turn out to be correct, but I take off points because you've just said it's 0 without any proof, right? Without any evidence. So this is, we know the form of this limit is negative infinity times 0. And I know my Cal class, someone in my Cal class is going to make me happy here by telling me what the technique is when you see this. What do we do though? You drop one down. Very good. You take one of these factors and you drop it to the denominator. That's the technique. Now, what does that mean? Drop it. This is what it means. I need to erase. So I'm going to come over here. We pick one of these two factors and we push it to the denominator. So I think for me, the thing that looks easiest is to leave the e to the t on top. And on the bottom, I push the t down. When I push the t down, I can't just put a t on the bottom. What I really mean is I'm writing 1 over t on the bottom. Do you all agree that this is the same expression as this?
Yes.
Right? Because you can just flip that t back up there.
Oh, okay.
Right? But the reason why we do that is because now if you take the limit, where's that going again? We already said what e to the t does when you go to negative infinity. Where does it go? 0. And now, careful, what does 1 over negative infinity do? It goes to 0 as well, right? 1 on top, big denominator, goes to 0. Yes? And now you have a limit that looks like 0 over 0. And that you can use L'Hopital's rule on. Right? You can only use L'Hopital when you have a ratio. It's got to be 0 over 0 or infinity over infinity. So I need to continue, but I'm running into my own work here. So I'm going to say all of that. Here's where I am now. I'm going to use L'Hopital's rule. I usually put an L with a circle around it. Some textbooks use an H with a circle. Some textbooks just put an L. Some textbooks just put an H. But I need to somehow tell you what I'm doing, right? So that's the indication to you, the reader, that I am now applying L'Hopital's rule. And L'Hopital's rule says that, what do?
Go to the top of the
You do the derivative of the top over the derivative of the bottom. What's the derivative of the top? E to the t over -1 over t squared. So the derivative of this, remember, that's really t to the -1. And so you take derivative of that, you get negative t to the -2, because you subtract 1 from the power, and that turns into this. Did that help? Did that solve anything? What happens? As t goes to -infinity, that goes to where? So that goes to 0, right, still? And this goes to where? 0.
It's going to be like that.
It didn't, and then if we did it again, it's going to keep doing this, isn't it? Like I'll get e to the t on the top, and on the bottom I think next time I'm going to get like a positive 2 over t cubed. And then next time it's just, I'm going to get stuck, I'm stuck.
So would you say that like all that first interval it diverges? Like,
Nope. Nope. I'm not going to say that, I'm not going to give up.
The other one on top.
Yeah, so I dropped the t, didn't I? Because that's normally the one that is going to help us. But now I'm going to change my mind. And I'm going to drop the other one instead. And I'm going to leave the t on top and drop the e to the t to the bottom.
So when you drop it, are you going to have to drop it as 1 over e to the t? Or since it's a negative exponent? Is it
Either way. Either way.
Okay.
Either way. So I'm going to say here, I'm going to say stop, right? I'm just, this isn't going anywhere, right? Okay. So do you see why I get frustrated when students skip this step? This is not a trivial thing. To say this is 0 is not trivial. There's work involved. And you have to understand a lot of things, right? A lot of things and how things work together. So I'm back at this right here, and I say, okay, I'm going to leave the t on top. Now the reason why t being left on top is a good thing is because when I take the derivative of it, it's going to be 1, right? So that, maybe I should have thought about that to begin with. But you know what? You know, we learned, right?
so that would be the denominator should always be, well, would the denominator always be 0?
I don't want to say always, well, I'm not even sure what I'm saying. I'm leaving the t on top, okay? I'm leaving t on top. And now how do you drop the e to the t down? There's kind of 2 different ways to look at this. One way is to look at it as e to the -t. Right? Isn't that the same as e to the t on top? Having e to the -t on the bottom? You could also look at it as 1 over e to the t on the bottom. Either way.
If we can get it that way, it's just going to flip the sign on your infinity?
It's just going to flip what?
The sign on your infinity? So,
This way, looking at it this way?
Yeah.
Yeah, it's just going to flip the sign on my infinity.
okay.
So I'm going to go with this, all right? So if I let t go to -infinity right now, where does the top go? Where does the top go? -infinity, right? Over, okay, now this is what we're saying. If you let t go to -infinity, if I plug in a negative number right there, and it already has a negative here, that becomes positive, doesn't it? So this is really now saying what happens to the e function as you go to positive infinity. So look at this graph, and what happens as you go to positive infinity? It goes to infinity. So your bottom goes to infinity as well. We need that for L'Hopital, don't we? We need that for L'Hopital. So now I can apply L'Hopital. Limit t goes to -infinity. Okay, derivative of the top is 1, and the derivative of the bottom, negative e to the -t. So there's a little chain rule involved there, right? The derivative of e to anything is itself, but then you have to take derivative of what's up here. Derivative of what's up there is -1, and that's why there's a negative in front of this. Right? What's wrong? Come on. You got it. You got to let me know. Right? Try this limit again and see what happens. Well, the top is 1, isn't it? That's not going anywhere. That is 1. And now I'm really hoping the denominator goes to infinity, because if it does, 1 over infinity is going to go to 0. So that right there, if I let t go to -infinity, a double negative is positive. So this is going to e to the positive infinity, which we said is going to infinity, and there's a negative in front. The negative doesn't matter. A fixed number divided by a number that gets huge goes to 0. Finally, I know what happens there, right? Coming back to my work. Equals. I've applied the limit. I had -1 here. Minus, and then this right here, we just determined goes to 0. Okay. Plus. Shit. Think about what happens. R is going to positive infinity, not negative infinity. So that goes to what? Infinity times, what's e to the infinity? Infinity. What's infinity times infinity? Infinity. Minus infinity. Infinity minus infinity is indeterminate form. It's not 0. It's an indeterminate form. So we have to go figure out what that limit is.
So now, so you can't just say we had one that looked just like it and then try to like.
Well, they do look just the same, but this goes to positive infinity and that one went to negative. That makes a big difference on things, right? It does? Because if I plug negative infinity in here, that goes to 0, doesn't it? But if I plug positive infinity in here, it goes to infinity. Right? Do you see? Because you're going 2 different directions on the e to the e function? Yeah? Yes? Question?
How come, whenever we broke that up, how come you were allowed to drop off to minus e to t, and we only did the limit as t?
Because it went to 0.
Okay.
It wasn't a problem.
So that one we don't have to prove.
We don't have to worry about that.
Okay.
Yeah, that goes to
Okay.
0.
All right, gotcha.
Yeah, that did not give us an indeterminate form. So I've got a second limit to do here, right? I have a second limit to do. So I'm doing some scratch work on the side here. I need to figure out what the limit is as r goes to positive infinity of r e to the r minus e to the r. When I do that limit right now, I know I'm getting infinity minus infinity. That's what we get, infinity minus infinity. Do you all understand that? All right, my Cal 1 class. What's the standard technique when you have infinity minus infinity?
Factor out the
Factor something if you can. Factor if you can. All right? So is there something we can factor there? E to the r. Limit. R goes to infinity. Hey, if this L'Hopital is like, hey, I don't remember all this. I don't remember my teacher telling me, like, do this when you see this. Send me an email. I'll send you a link to my Cal 1 videos, and you can go watch the whole lecture on L'Hopital's rule that I have, all right? If you're interested. If this is all comfortable to you, then no worries. Okay. Now, does this help us? Well, where does this go? This is e to the infinity. That's huge, right? So this is now headed to infinity. And then times, what does this one go to? Infinity minus 1, which is infinity still, right?
Which is perfect.
But now you have infinity times infinity. And what's that?
L'Hopital's rule.
No. What's a huge number times a huge number? Huge number. See, there's no, this isn't like infinity times 0 where you're like, oh, who wins? This is big number times big number, right? Big number times big number is big number.
Sweet.
So this just goes to infinity, right? When you multiply 2 big numbers, you get a big number. When you subtract 2 big numbers, you don't know what's going on. Okay, so that's why we factor. We try and turn the subtraction into a multiplication so that we can determine what happens. Y'all good? Okay, so that means this over here, coming back, this goes to where? Infinity. Shit. Infinity plus 1. Infinity. What does this integral do? It diverges. See, we need this to be a nice finite number to say it converges, but it's becoming infinite. And therefore, our final answer is that that integral diverges. As soon as one of these goes to infinity, we're done. This integral diverges. All that work for that. Let's look at the graph of that. That's the graph. If you look at the graph, I think you might see from the graph that it kind of makes sense that this integral was going to diverge to begin with. Do y'all see it? Right? You're trying to find the area underneath the curve, between the curve and the x-axis. So we're trying to find that area, right? Out that way. And then over here, the area underneath the graph this way. Well, it's infinite, right? Now, do we know the area? Do we know the area from here over? We do, right? Because we did that integral that went from negative infinity to 0. And what did we get on that integral? Was it negative 1? Yeah, does it match? Does it make sense? I mean, the area is underneath the x-axis, so it's negative, but it actually has an area of 1, like if you look at it like a positive area. Yes?
Does the convergence or divergence of something hold as it goes up and down with integrals and derivatives? Like,
How do you mean?
so like if you took the integral again, would the next integral also?
Oh, okay. So you're asking, let's say you have a function that the area under it is convergent, right?
Yeah.
That you're asking if the antiderivative of that,
Yeah, like if the integral of the integral, would it then also?
would that also be, no, I don't think you can say that. I need to think of an example, but I don't think it would work.
E to the x, I think.
What's that?
I think you keep subtracting e to the x, right? So keep integrating by parts.
Yeah, but I don't think he's asking about that specific example necessarily. Just in general. Maybe for like maybe for this example, we would have some property fall through, but I don't think you can say that generally. I'm trying to think of a counterexample in my head right now, but I'm not coming up with something. Because you want something that maybe it converges, then you do the antiderivative, look under the area, and now it diverges, right? Yeah. Or the other way around. Let me think about it. All right. That was an interesting example. Lots of L'Hopital in there. Okay. So where do we see this concept, right? Like, why is this an important concept? This idea of these improper integrals where you go from negative infinity to infinity. So we're going to do a slight little tangent, go off course here, tangent, no pun intended, right? We're just going to go off, but it's important in sense of the big picture of things. So I want you to think about something for a moment. Let's say that I have a dice, you know what I'm talking about, right? 6-sided die, and I'm going to roll it, all right? And I want you to think about what the outcomes are, right? So the only outcomes on a 6-sided die, I'm going to list them here, the outcomes are going to be what? 1, 2, 3, 4, 5, and 6, right? Those are the only outcomes on a 6-sided die. So if I roll the die, what's the probability that you're going to get a 1? 1 out of 6, right? So on this y-axis, I'm going to put the probability that we get that 1. So I'm going to put here, this is 1/6, yes? So I can imagine that, let me draw it like this. I'm going to draw a box that goes up, over, down like that. That represents the probability of 1 happening. What's the probability that 2 happens? 1/6, the same, right? 1/6. Probability that 3 happens? Same thing, same thing, same thing, same thing. Now I have intentionally made these rectangles have a width of 1. So that's 1, 1, 1, 1, 1, 1. Okay? What is the total area of all those boxes? So 1/6, 1/6, like this is 1 times 1/6, 1 times 1/6, 1 times 1/6. So each one of them has an area of 1/6, right? So the total area would be 1. Yeah? So if I said, what's the probability of rolling a 3, you would say, what's the area of that box, right? If I say, what's the probability of rolling a 3 or a 4, you would say, oh, the area of those 2 boxes. Understand? What's the probability of rolling an odd number? Well, it's that box area, that box area, that box area, right? Yeah. What's the probability of rolling a 1, 2, 3, 4, 5, or a 6? 100%, which is the area of all of these, yes? Okay, that seemed pretty straightforward or no? Okay, this is an example of what we call a probability, I'm just going to put probability density function. It's a visualization of the probabilities of something, all right? And what we have down here, these values, are what we call discrete random variables. Anybody here taking a stats class? Not yet. Okay, discrete random variables. The important word here is the word discrete. Discrete random variables all have a very special property to them. If I ask you how old you are, you're going to give me an integer as an answer, right? You're not going to tell me you're, 21.357 years old, right? You're going to tell me you're 21 years old. If I ask you how many siblings you have, you're going to give me an integer answer. If we say how many cars are parked in the parking lot right now, you're going to give me an integer answer, right? Things like that are called discrete random variables. They are going to give you nice whole number answers. We have other types of variables that are called continuous random variables, right? That's the other kind. Random variables. Yeah, I'm getting to it. I'm getting to it. So what is a continuous random variable? Something like, let me see. You have a soda can here. How many ounces does it say it has on there? 12. Do you think if we actually measured it precisely, it would be dead on 12.00000? No way, right? If we had like the perfect measuring instrument, right? It's different than the number of siblings. Number of siblings, you don't have like 2.6, well, depends. Some of our siblings are not quite there, right, maybe, but you know what I mean? Right? So it's a different sort of variable because it can take on values that are not integers. So if I look at something like this, let's say this is the outcomes. I'm going to take some cans of soda, right? And I'm going to measure the number of ounces in them with a very, very high precision instrument, right? And then I'm going to have over here the probability that you actually hit that, right? What we should expect to see at 12, that's 12 ounces, right? Is that we're probably not going to ever be dead on 12, right? I mean, it would be practically impossible to be dead on 12. That's 12.0000 forever, right? So I'm not going to draw a rectangle here because it doesn't make any sense to measure something to that precision. But what I can do is give you a little window, can't I? Like this infinitesimally small window, which is exactly what we were doing with the Riemann sums, right? These rectangles that became infinitely thin. Same idea. Imagine you have an infinitely thin rectangle right there. So it's like we're doing this little window where it's 12 plus a little bit, 12 minus a little bit. Do you agree that the probability should be pretty high that it's going to lie in this really tiny window? Yeah? And if I go, let's say this is 13 ounces, and this is, let's say, 11 ounces. I think we would agree that the probabilities over here would be pretty small, wouldn't they? But we should expect that it goes, if we were to continue doing rectangles, we should expect to see something that goes like this, and then comes back down like that. That looks, if I were to look at it like a function, like a curve, it would be like that, right? Now, we could say it'd probably go here, and I think 0 negatives would make no sense, right, to us? And the probability that we get something at 13 is probably pretty low, yes? With all probability density functions, whether or not it be discrete random variables or continuous random variables, we want the total probability of all possibilities, right? The total probability to be what? 100%. Which means that we want the area of all of these to be 1. And for a continuous random variable, we want the area under this function to be what? 1. Right? So that is the property of a probability density function is that if you graph the probability density function and you look at the total area underneath it, it needs to be 1 to be considered a probability density function. Yeah?
Is that just kind of like an M shape where it kind of goes up and then the perfect number is kind of just
No, it's there because it's a window. It's a window. We're saying there's a small window.
like a small split kind of thing?
For something like that, what we would say is what's the probability that that can is going to, we would never say what's the probability that the can is going to be 12 ounces exactly. We would never say that. We'd say what's the probability that that can is between 11.9 and 12.1 ounces. And then you can define that probability because it would be the area on that little definite integral from 11.9 to 12.1. And you'd find the area under the function. Understand? Okay, so the most important probability density function, the one that you would see maybe in the future, is this one right here. It is called the standard normal distribution. It looks horrific, but let's just look at it. It's e to this. Now, x is the variable. Mu and sigma are just constants. And they actually represent, mu is the mean or the average of your data set, and this sigma is your standard deviation. That's not important. If you graph this function, here's what it looks like. Well, why is it so damn big? Let me make this smaller. Oh, yeah. Yeah, I guess that's good. This is me adjusting. I'm adjusting right now the standard deviation, and I'm adjusting the mu, which is the average. So let me go, we're talking about that can, I'm not going to be able to do it. But we were over here somewhere, right? So this standard normal distribution, you've probably heard this referred to as the bell curve, right? This is the bell curve, maybe not, maybe. Okay, so there's a law in statistics, it's called the law of large numbers. And it says that if you take a data set, no matter what you're measuring, the height of people, the age of people, whatever it is, number of siblings, whatever you want to measure, if you do a large enough sample, your distribution should look normal. It should look like a normal distribution. Like, all people lie within certain height, right? And then you have some outliers, right? You have people that are really short, you have people that are really tall, but you should get an average. If I measure in here the heights, it's not going to look like that, right? It's going to look, it'll depend. But if you get a large enough sample, it should start to look like the standard normal distribution.
So that's not the law of averages, that's the law of, you said large numbers.
Law of large numbers, yes. Law of large numbers. Anyways, how is this related to us? That function right there, if you were to integrate this, if you were to actually integrate this from negative infinity to infinity, the answer is 1. And that's because the total area under that function must be 1 to represent the probability of all possible things that could happen. All right? Now, integrating that is actually impossible for us to do without series. We have to have series to be able to do that. And if we just ignore the constants, ignore that constant, ignore that constant, ignore that constant, this really looks a lot like this function right here. And that's impossible for us to do. We do not have a technique of integration to do that. So we're stuck. But that's the standard normal distribution, and that's all. I just wanted y'all to see it. Like, we're talking about areas under curves going both directions. Where would you ever see that? We see it in statistics. Who's taking statistics? Anyone? Do you remember using like z-tables in the back of the book? Basically, a z-table is essentially a table that they've already found the areas using they've already found the integral for you, and they have the values listed. So if you stay between two numbers, it's calculating that area, so you don't have to. That's all it is. All right, we move on. We're still here in this section, okay? We're not. Remember, this section had 2 parts, right? This section had 2 parts. We're still in the first part. A nice formula. I would like us to show that if you ever do the integral from 1 to infinity, of 1 divided by x being raised to a power, I want us to show that this will diverge always if p is less than or equal to 1, and it will converge if p is bigger than 1. Split where? But p is not our. We're not integrating like from 1 to p. P is the power on the x.
Is this just a property?
Yeah, we're going to show it. So look, if you go back in your notes, the very first problem I did in class for this topic was this one. I did that problem. That was the first one we did when we started talking about this last class. And what we found is that this diverged. It was divergent. And then the next example I did after that was this one. And when we did that, it converged. Right?
Yeah, that was the one that it wasn't intuitive. Or rather, it was counterintuitive.
Yeah, because they both looked the same, but one of them converged, the other one didn't, right? This property is saying that the power that you see on the x, this power is a 1, this power was a 2, that power dictates your convergence or divergence. If the power is bigger than 1, you're going to get convergence. But it's less than or equal to 1, you're going to get divergence. And we need to show that, all right? We're going to prove that this is true. Before I do it, though, let me see, what do I want to... Hold on, let me think about this for a second. I think we can do it without me. I can address it when we get to it. I don't need to do it separately. All right.
Does that technically say that the integral from 1 to infinity of 1 is divergent?
With that.
Because if you have x, if p equals 0.
Yeah, if p is 0, right, then this would be 1 over 1. So you're integrating under the constant 1 function. What would the constant 1 function look like? It would look like that, right? And then now the area under that would be infinite, so it'd be divergent. I think that's what you're saying, yeah? Yeah. And not only that, but what if p was negative 2? Then what is that? If p was negative 2, what is that function really? X squared. And think about what x squared looks like, and the area under that would be infinite as well, right? So this is going to cover everything for us. But we have to prove it, okay? We have to show it. So here we go. We're going to show it. And I'll just tell you, at the end of the day, you just need to know that this is true. Okay, you don't ever need to prove this, but we're Cal 2 students, right? We should see maybe where this comes from, yeah? Think we can handle it? All right, so here's what I'm going to do. I'm going to do the limit. T goes to infinity of the integral from 1 to t of 1 over x to the p dx. Right, so that's just me knowing this is an improper integral. I have infinity as one of the limits. I replace that infinity with t, and I'm going to let that t go to infinity. Now I need the antiderivative, right? I need the antiderivative of this. So let me do some scratch work over here. I'm trying to find the antiderivative of x to the 1 over x to the p, right? I'm going to rewrite that as x to the negative p.